All right, so our last gas law lesson. This one is about the ideal gas law. And this is the one rule to rule them all. Okay, so this is the law that goes over and combines all the other laws we've learnt about. In particular, it includes Avogadro's law on the moles of gases into our combined gas equation. So our ideal gas law states that pressure times volume is equal to the moles times R, which is a gas constant, times the temperature. So the gas constant is given to you, and it has the value of 8.314 joules per mole per Kelvin. Okay, now the thing is about these two ones, this is going to be the easier bit to do, because out of remembering all the other ones, these two are actually given to you on your data sheet. So the formula page, your data sheet has a periodic table, and it's actually 4 pages. On one of the sheets, it has the formulas. So it's got our moles formula, it's got our concentration, and here you can see it's got our PV equals nRT, which is ideal gas law. And also, if you have a look down underneath those, you've got your Avogadro's constant, you've got your molar volumes, molar gas volumes, and you have your gas constant here. Okay, so these are what we're going to look at. And gas constant, sorry, the value is R, and I'm sure it's going to jump down, so I did it there. All right, so let's just use this in an example. All right, I should actually go back for a sec. Wait, ideal gas. So for a gas to be ideal, it should basically the volume of the particles the particles shouldn't have any volume, which of course they do have volume. All matter has volume, but the volume of particles in a gas is insignificant compared to the volume of the gases taking up. They're so far apart. So that's the first part of it. And the second part is the interactions. So they should have basically no interactions with each other. And because the particles in gas are so far apart, they really don't have an effect on each other very much, unless it's at very low temperatures or at very high pressures, when of course they're all pushed together. There are interactions there. So basically all gases do show this in those with it outside of the low temperature and high pressure sort of thing. And the gases that do it the best are hydrogen and helium gases, because they are the smallest. Helium in particular has the least interactions with any of the other gases, with its particles than any of the other gases. It's hasn't got very many electrons, so there's not too much of a different density moving around. It's very lightweight, so it basically, just a few degrees above absolute zero, it becomes a gas. So it's one of the best ones to do with this. But basically, we'll use this with all our gas laws, with all our gases to do this. So what we're going to do here, and I've gone to typing because my computer is not quite working so well. Okay, so what is the volume in litres occupied by 13 moles of carbon dioxide gas if the pressure, so that is M, if the pressure P is 250 kilopascals and the temperature is 75 degrees Celsius. All right, so let's see what we've got. We've got pressure, 250 kilopascals. Volume, we're looking for that. N is equal to 13.0 moles. See, I knew that's exactly what's been happening. And temperature equals 75 OIS. That's how I get it in, degrees Celsius. And if I add 273 equals 314 348 Kelvin. All right, and then we have R, and R is the value that is just what it is, 8.314. Okay, and that is the joules per Kelvin. I won't put all that in because it will take too long right now. All right, so with this now, let's see if I can write it in the middle. PV equals nRT. See. Anyway, all right, so we're looking for volume. So we divide this side by P, divide this side by P. V, sorry guys, I think it's just tired of me doing this. Okay, so basically volume equals nRT divided by P. So we just substitute everything in. 13.0 plus, I'll just put this in, 13.0 plus, sorry, it's multiplied by 8.314 times 348. And all that divided by 250. Okay, if we put all that in, oops, where's my calculator? Here we go. 13 point, oh, let's just go back, put this in. 13.0 times, what was the next one? Go this side now. 8.314 times, oops, for some reason that's all doing funny stuff. Let's try again. Parentheses, 13 times 8.314 times 348, close the parenthesis, divided by 250 equals 150.45. So 150. To round it to three significant figures, 150 litres. Okay, so from that we were just basically plugging in all the different values we've got. So what I need you guys to do now is actually just work through some of these questions, and I'm going to then put up a quiz to get you to practice and show me what you know. So it's very hard for me to get you to type up all your calculations. I'm going to ask you to do photographs and upload those, or I'm going to ask you to do quizzes and that for me so I can check how you're going with your calculations. Don't forget to ask me if you're not sure what you're doing, and and I'll be able to help you with those things. Basically, this is the end of this topic. Okay, and what we're going to do is move on to next week, look at different reactions and explore. Actually, sorry, before we do that, I've got an experiment I'm going to do at home, film it and show you, and then we're going to move on to the next topic on reactive chemistry. All right, that's it for now.